CalTech. He started in particle theory, where he made a name for himself on cosmological predictions of super heavy magnetic monopoles, which then had important influence for inflation theories. And then in 1990, maybe he saw the light and he decided to start working and thinking about quantum computation, quantum information, and also solving otherwise intractable problems. He's a member of the National Academy of Sciences. He's the director of the Institute for Quantum Information at CalTech, and he's also known in the popular press for having Hawking concede a bet to him, a famous bet on information paradox. Without further ado, I give you John Preskill.
I got a couple of feet to play around with. All right, well, thanks a lot, Spee, and it's a great pleasure to be here. This is going to be a talk about quantum physics and also about information. Now, we all recognize that we have information technologies that have transformed our lives in many ways, but we're aware that the technology that seems impressive today is going to be replaced in the future by new technology that we can't really expect to imagine today. It's interesting just the same to speculate about future technology. I may not be the ideal person to engage in that type of speculation. I'm not an engineer, I'm just a theoretical physicist, and maybe not particularly knowledgeable about how computers really work. But as a physicist, I know that the crowning intellectual achievement of the 20th century was the development of quantum theory, and it's natural for a physicist to wonder how the development of quantum theory in the 20th century will impact 21st century technology. Quantum theory is an old subject by now, but some of the important ways in which quantum and classical systems differ from one another we've begun to appreciate only relatively recently. To a physicist, information is something that we can encode and store in the state of a physical system, like the pages of a book. But fundamentally, all physical systems are really quantum systems, ruled by quantum physics, and therefore information is something that we can encode and store in a quantum state. And information carried by quantum systems has some notoriously counterintuitive properties. That's why we like to speak about the weirdness of quantum theory. And as physicists, we relish that weirdness and find it delightful, but we're also beginning to ask more seriously whether we can put the weirdness to work to take advantage of the unusual properties of quantum information to perform tasks that wouldn't be possible if this were a less weird classical world. And that desire to put weirdness to work has driven the emergence of a field we call quantum information science, which gets much of its intellectual vitality from three central ideas: quantum entanglement, quantum computing, and quantum error correction. And the goal of this talk is to explain those ideas. So I'd like to start at the beginning. As you know, any amount of classical information can be expressed in terms of indivisible units, bits of information, where we might envision a bit as an object, like a ball, which can be either one of two colors, like, say, red or green. And I can store a bit in a box, and then later on, when I open the box, the color ball that I put in comes out again, so you can recover the bit and read it. Now, quantum information carried by a quantum system, can also be expressed in terms of indivisible units, what we call qubits or quantum bits. And in the case of a qubit, we can again think of the object or envision it as a colored ball stored inside a box, but where we can open that box through either one of two complementary doors, which correspond to two different ways in which we could prepare or observe the state of the qubit. And I can put a ball inside a quantum box through either door number one or door number two, and then later on, if I open the same door again, the color that I put in comes out again, just as though the information were classical. But if instead we store information in door number 1 and then close the box and open door number 2, observe the qubit in a complementary way, then what comes out is uniformly random, has an equal probability of being either red or green, and we have no way to predict what color we'll find until we open the box. So to read quantum information, you have to do it the right way. If you open the wrong door, you will inevitably damage the information. And we can appreciate one consequence of that. If we ask, what would be involved in copying quantum information? If I had a perfect quantum copy machine, that would mean I could store information through door number 1 of a qubit and make a copy of the qubit. And then if I open door number 1 on both the original and the duplicate, the color I put in would come out of both boxes. And if, on the other hand, I put information into the qubit through door number 2 and made a copy, I could open door number 2 on the original and the duplicate, and the color I put in would come out of both boxes. But in fact, there's no such machine. It's not possible under the rules of quantum mechanics to build a copier which can perfectly copy unknown quantum states. And the reason for that is that to make the copy, the copier would have to probe inside the box. And if it happened to use the same door that I had used, it would be able to copy the information just as though it were classical. But if it uses the wrong door, that would damage the information, and there would be no way to make a high-fidelity copy. So we might be able to clone a sheep, but we can't clone a qubit. So as you've seen, I like to think about these qubits in kind of an abstract way. But in fact, qubits are always realized physically in some kind of physical system, and I'll mention some other examples later. But just so we have something concrete to think about, we could imagine encoding a qubit in the polarization state of a single particle of light, a single photon. The polarization meaning the axis along which the electric field of the photon oscillates, having the polarization or electric field oriented either horizontally or vertically correspond to the 2 states we could see through door number 1, and polarization along these 45-degree rotated axes correspond to what we would see if we opened door number 2. So I could, for example, prepare a photon in the horizontally polarized state and then observe the polarization along the tilted axes, and what I would observe is just a random bit, with the 2 outcomes being equal probable. Now, the really interesting ways in which quantum information differs from classical information can be appreciated only if we think about systems with more than 1 qubit. So let's suppose we have 2 qubits. They could be far apart from one another, one in my lab in Pasadena, the other in the custody of my friend who lives in the Andromeda Galaxy. And some time ago, these 2 qubits were both on Earth, and they interacted in some way that caused them to become correlated with one another. So that pair of qubits is now in a state with some interesting properties. Namely, I can open my box in Pasadena through door number 1 or door number 2, and either way, I just find a random bit. Probability 50% of being red, 50% of being green. And the same is true for my friend in Andromeda. He can open his box through door number 1 or door number 2, and he just observes a random bit. So neither one of us, by opening our boxes, acquires any information about what's inside the boxes. We just generate random bits. And that seems peculiar because with 2 qubits, we should be able to store 2 bits of information, but we don't see here where that information is hiding. Well, the answer to where the information is for this particular state of the 2 boxes is that it's entirely encoded in the correlations between the qubit in Pasadena and the qubit in Andromeda. Namely, if I open door number 1 and my friend also opens door number 1, we're guaranteed to find balls of the same color. Could be red or could be green, but the same color if we both open door number 1. And same thing if we both open door number 2. The color that we see has probability 1/2 of being either red or green, but when we both open door number 2, we see the same color. So there are actually 4 distinguishable ways in which the qubit in Pasadena and the qubit in Andromeda could be correlated with one another. We could see either the same color or opposite colors when we both open door number 1 or both open door number 2. And by choosing one of those 4, we've encoded 2 bits of information in the boxes, one of 4 possibilities. But what's unusual in this case is that that information is inaccessible locally when you look at the boxes one at a time. It is encoded non-locally between these 2 distantly separated boxes. And that feature of quantum information, that it can be non-locally encoded so that it's inaccessible locally when we open one box at a time, that's what we call quantum entanglement. And it's the really crucial feature that distinguishes quantum information from classical information. Now, correlations themselves are nothing unusual. We encounter them all the time in daily life. My socks are usually the same color, so when you look at one of my feet and observe the color of my sock, you know without looking what color sock to expect on the other foot. And it's sort of similar with the boxes. If I want to know what my friend in Andromeda is going to see when he opens door number 1, I can open door number 1 in Pasadena to find out. If I want to know what my friend will see when he opens door number 2 in Andromeda, I open door number 2 in Pasadena to find out. So it might seem that really the boxes are just like the sockses, that there's nothing new here. But I insist the boxes really are different than the sockses. And the essence of the difference is that there's just one way to look at a sock. But because we have these 2 complementary ways of looking at a qubit, the correlations among qubits are richer and far more interesting than correlations among bits. Now, this idea of quantum entanglement was first explicitly discussed in a famous paper by Einstein and collaborators way back in 1935. And to Einstein, quantum entanglement was something so unsettling as to indicate that something is missing from our current understanding of the quantum description of nature. Now, that paper elicited some interesting responses, including one from Schrödinger, which was especially insightful. And Schrödinger put it this way. He said, the best possible knowledge of a whole does not necessarily include the best possible knowledge of its parts. So what Schrödinger meant is that even if we know precisely how the state of that pair of separated qubits was prepared, we're still powerless to predict what we'll see when we open the qubits one at a time through door number 1 or door number 2. And it was Schrödinger who suggested calling this unusual correlation entanglement. He also said it is rather discomforting that the theory should allow a system to be steered or piloted into one or the other type of state at the experimenter's mercy in spite of his having no access to it. What Schrödinger meant is that it seems rather peculiar that I, by opening either door number 1 or door number 2 in Pasadena, will get to find out what my friend will see when he opens either door number 1 or door number 2 in Andromeda, even though these boxes are a galaxy apart from one another. But Schrödinger understood that these correlations, though different from ordinary classical correlations, do not allow instantaneous communication between Pasadena and Andromeda. When my friend in Andromeda opens his box, he just finds a random bit, no matter what I did in Pasadena, so no information about the action I took on my box in Pasadena is conveyed to my friend when he opens his box. Now, this idea of quantum entanglement did not advance very much for the next 30 years until the work of John Bell in the 1960s. And with Bell, we began to think about entanglement in a somewhat different way, not just as something very weird, but as something potentially useful, as a resource that can be exploited to perform tasks that wouldn't otherwise be possible. I'm not going to go into the details. What Bell described can be thought of as a game that 2 players play. These 2 players, Alice and Bob, are in different labs. And the way the game works is that Alice and Bob receive inputs, and their objective is to produce outputs that are correlated in some way that depends on the inputs that they received. But the rules of the game are such that Alice and Bob are not allowed to communicate with one another between when they receive those inputs and when they produce their outputs, though they are allowed to use correlated pairs of bits that could have been distributed to them before the game began. And for this particular version of the game, if they play the best possible strategy, they can win the game with a probability of success, so 75% if we average uniformly over the inputs they could receive. But there's also a quantum version of this game. And in the quantum version, the rules are exactly the same, except for one thing. Now Alice and Bob are allowed to use entangled pairs of qubits that were distributed to them before the game began, and in that case, they can play a better quantum strategy, exploiting that entanglement, and win the game with the higher probability of success, about 85% instead of 75%. So they've used the entanglement as a resource to perform a task, in this case, winning the game, better than they could have if they didn't have quantum entanglement. And experimental physicists have been playing this game for decades now, and winning with that higher probability of success, which Bell pointed out the rules of quantum mechanics allow. So these non-classical correlations really are part of nature's design. Einstein had derided quantum entanglement. He called it spooky action at a distance, which sounds especially derisive when you say it in German. But it doesn't matter what Einstein thinks. Nature is the way experiments reveal her to be, and we should learn to love her the way she really is. So the boxes are not like the sizes. With quantum entanglement, I can win a game with a probability of 85% instead of 75%. Is that really such a big deal? Yeah, it really is quite a big deal. And to understand its significance, it's helpful to think about systems with many parts. We might imagine a book which is 100 pages long. And if that book were classical, I could read the pages of the book one at a time. And every time I read another page, I would learn another 1% of the content of the book. And after I've read all the pages one by one, I would know everything that's in the book. But suppose, on the other hand, it's a quantum book. It's written in qubits, not in ordinary bits, and the pages are very highly entangled with one another. Well, that would mean that when you look at the pages one at a time, you would just see random gibberish, which would tell you essentially nothing, that distinguishes one highly entangled book from another. And that's because the information in the book is not encoded in the individual pages. It's encoded almost entirely in how the pages are correlated with one another. To read the book, you would have to make a collective observation on many pages at once. That's quantum entanglement. And it turns out that these correlations among the parts of the system are extremely complex to describe using ordinary classical data. So with a rather modest number of qubits, just 300 or so, if these qubits are in a typical highly entangled state, to give you a complete description of all the ways in which the qubits are correlated with one another, I would have to write down more bits than the number of atoms in the visible universe. The description would be so complex that we could never imagine writing that description down, even in principle. And that property of quantum information, that it's too complex to describe using classical information, was very intriguing to the CalTech physicist Richard Feynman. And it led him in the early 1980s to make a suggestion that if we were able to build a computer that operates on qubits rather than classical bits, a quantum computer, it ought to be able to perform tasks that surpass what we could do with any digital computer. Feynman's idea was that if we can't even describe in terms of ordinary bits the content of a few hundred qubits, then perhaps by processing the qubits, we'd be able to perform a task that a classical computer would never be able to emulate. And that idea was realized in a rather spectacular way by Peter Shor in the 1990s. Shor studied the problem of finding the prime factors of a large composite integer. This is a hard problem for digital computers with a complexity that scales very unfavorably with the number of bits in the numbers, so that in practice it's intractable to factor numbers that are much longer than, say, 1,000 bits long. But Shor pointed out that if we had a quantum computer, this would become an easy problem, not much harder. than multiplying numbers together to find their product. And when I heard about this in 1994, I was really awestruck because I realized what it means is the difference between hard and easy problems, between problems that we expect to be able to solve eventually with advanced technologies, and problems that we'll never be able to solve because they're too intrinsically hard. That boundary is different than it otherwise would be because we live in a quantum world instead of a classical world. I thought that was one of the most interesting ideas I'd encountered in my scientific life, and thinking about it eventually led me to steer the direction of my own research from elementary particle physics to quantum computing. Does anybody care whether factoring is a hard problem or not? Yes, there are people who care, because the security of the crypto systems that we all use to communicate privately over the internet are based on the presumed hardness of factoring and other related number theoretic problems. In the decades to come, when quantum computers are widely available, we won't be able to protect our privacy in that way. Alternatives exist, but it's still unclear what is going to be the best way to protect our privacy in the coming post-quantum world. The important thing we learn from Shor is that there's a very intriguing classification of problems. There exist problems which are hard for classical computers, but easy for quantum computers. It becomes a compelling question to understand better what are the problems in this region of intermediate difficulty, quantumly easy, but classically hard. And we've learned some things about that in the last 20 years, but I think we have much more still to learn about it. From our present perspective, in particular from the perspective of a physicist, what's particularly notable about quantum computing is we expect that with quantum computers we'd be able to efficiently simulate any process that occurs in nature. And we don't think that's true of digital computers, which are not able to efficiently simulate highly entangled quantum systems. And so that means with quantum computers we'd be able to probe more deeply into the properties of complex molecules and exotic materials, and we'd also be able to explore fundamental physics questions in new ways, for example, by simulating high-energy collisions of elementary particles, or the quantum behavior of a black hole, or the universe right after the Big Bang. So we've been trying to develop quantum algorithms now for more than 20 years since Shor's breakthrough, and a number of algorithms have been discovered. One colleague of mine who's made very important contributions to that subject is Eddie Farhi, also a former particle theorist. And some years back, when one of his breakthrough papers appeared, I was moved to send him a poem, which began, "We're very sorry, Eddie Farhi, your algorithm's quantum. Can't run it on those mean machines until we've actually got them," and so on. I won't read you the rest of the poem, but you get the idea that there are many interesting theoretical proposals for how we can use quantum computers, but we can't carry out those proposals today because we don't have quantum computers that are sufficiently powerful to run those applications. So why is that? Why has it taken so long? It's been 37 years since Feynman issued his call to action, and we still don't have large-scale quantum computers adequate to run interesting applications. Well, it's really, really hard to build quantum computers. What is it that makes it so hard? Well, one fundamental issue is what we call decoherence. Physicists like to imagine the quantum state of a cat, which is both alive and dead at the same time. But in ordinary life, we don't see that type of superposition of macroscopically distinguishable states. And we understand why that's true. It's because a real cat, prepared in such a delicate superposition, would immediately interact with the surroundings, and that interaction with the environment would, in effect, immediately measure the cat, projecting it onto a state which is either completely dead or completely alive. That's what we call decoherence. And that phenomenon of decoherence helps us to understand why, even though quantum mechanics holds sway in the microscopic world, nevertheless, classical physics provides a quite adequate description of our ordinary experience of the macroscopic world. A quantum computer won't be much like a cat, except that although we will try hard to prevent it, in the lab it will inevitably interact with its environment in some way, and those interactions will drive decoherence, which can lead to failure of a quantum computation. So we don't expect to be able to operate large-scale quantum computers to solve hard problems unless we have a way of protecting the quantum computer for decoherence and other sources of error. Of course, errors can be a problem even in ordinary life, in the classical world. We all have bits that we cherish, that we'd like to store reliably. Everywhere it seems there are dragons lurking who delight in tampering with our bits. But we've learned ways of fending off the dragons. If I have some bit which I particularly cherish, I can store backup copies of the bit. And then a dragon might come along every once in a while and change the color of the ball. But as long as the dragon hasn't had a chance to change the color of 2 out of the 3 balls, I can ask a busy beaver to frequently check. And whenever he sees one ball a different color from the other 2, he recolors that ball, so all 3 match again. So by redundantly storing the information in this simple way, we can protect it against damage due to errors. And we'd like to use the same concept that redundant storage of information allows us to protect against error in the quantum world, but there are subtleties. As already noted, we can't make perfect copies of unknown quantum states. So I can't make a backup copy of the state of a quantum computer in the middle of a computation in case the original gets damaged. And furthermore, in the case of quantum information, there are more things that can go wrong than in the classical case. If I have a qubit, the dragon might open door number 1 and change the color of the ball and then close the box again. And that would be like a bit flip error that occurs in classical data. But alternative, a dragon might open door number 2 of the box and flip the color and reclose the box. That's what we call a phase error in the quantum data, which has no classical analog. But we need to be able to protect our quantum data against both the bit flips and the phase errors. There's another way of thinking about these phase errors, which is that the dragon might open door number 1 of the box, and instead of flipping the color of the qubit, just observe and remember the color. And the effect of that would be to change the value of the qubit when absorbed through door number 2. So since in many physical situations, it's easier for the environment to remember a bit than to flip a bit, these phase errors are particularly pervasive in a number of physical settings, and we need a way of controlling them. So the essence of the problem is that if we're going to resist decoherence, we have to prevent the environment from learning about the state of the quantum computer. Because if the environment is able, so to speak, to observe the state of the quantum computer, that will inevitably disturb it. So really, we need to keep the information that's being processed nearly perfectly isolated from the outside world. And that sounds impossible, because our hardware is never going to be perfect. But we've learned how to do it using the concept we call quantum error correction. And the essential trick is to use quantum entanglement. If I have a single qubit that I'd like to protect from damage, I can store that qubit in an entangled state of many physical qubits in such a way that if I look at those physical qubits one at a time, the encoded information is completely inaccessible. Just like with that 100-page book where you couldn't learn anything by looking at the pages one at a time. And so a dragon might come along and manipulate one of the physical qubits or observe it in some way, but the dragon won't acquire any information about the stored encoded data and therefore won't disturb it because the information is inaccessible when we look at one qubit at a time. So that's the essential idea of quantum error correction, to store the information in a highly entangled state so that the information is invisible locally and therefore resistant to local interactions between our data and the environment. The beaver can make collective observations without knowing in advance which qubit has been tampered with by the dragon, determine the nature of the damage that that dragon performed, and then reverse the damage. So we can redundantly store the information in a way that protects it against error, even in the quantum case, if we store it in an entangled form. So really, the idea is that the information that we want to protect is stored in a complicated system with many parts in such a way that when you look at the parts one at a time, the information is invisible, just like with that 100-page book we considered earlier. And that means when the environment interacts with the pages one at a time, it doesn't access or damage the information. And furthermore, we've learned how quantum information in this entangled form can be processed, so we can perform quantum computation while maintaining that protection. So we may not ever see an actual cat in a superposition of alive and dead, but in the not-too-distant future, we expect to be able to prepare an encoded state of a cat, which is both alive and dead at the same time, and maintain that delicate superposition state in a quantum memory for as long as we please. Now, when we were developing the principles of quantum error correction in the mid-1990s, it was an exciting time. One of my students at the time was Daniel Gottesman, and he was inspired to write a quantum error correction sonnet. And I'll only read 4 lines from that sonnet. We cannot clone perforce, instead we split coherence to protect it from that wrong that would destroy our valued quantum bit and make our computation take too long. And the sonnet goes on, but you get the idea. We were quite excited about this idea of quantum error correction. It seemed mathematically very beautiful, but it was really ahead of its time because the technology didn't exist 20 years ago to realize quantum error correction in the laboratory. But we've reached the point now where the technology is sufficiently mature so that quantum error correction can be realized in the lab, at least at relatively small scales. Now, a hero of this subject is my CalTech colleague, Alexei Kitaev. The day that we first met, when Alexei made his first visit to CalTech in 1997, was an extremely exciting day for me because when I talked to him and heard his seminar, I realized that Kitaev had an idea about quantum error correction, which is potentially transformative. The key thing that I learned from Kitaev is the connection between quantum error correction and topology. Topology is a word that mathematicians and physicists use to describe properties of an object which remain invariant if we smoothly deform the object without ripping or tearing it. And when we think about coherently processing the protected quantum information in a quantum computer, we would like the processing that we're performing to remain invariant when we deform the quantum computer by introducing some noise. So it makes sense to use topological principles to process the information. And we know in physics of interactions which have a topological character. For example, the Aharonov-Bohm effect, which asserts that I can have an electrically charged particle, like an electron, and transport it around a tube of magnetic flux, and that causes the quantum state of the electron to change in a certain way, which depends on the enclosed flux, even though the electron never directly visits the region where the magnetic field is non-zero. And furthermore, that change in the electron state is a topological property. It is no different if we deform the trajectory of the electron going around the flux tube. The only thing that matters is its winding number, that it wound once around the tube. Now, if we have a system in 2 spatial dimensions, which might be realized physically as a layer between 2 slabs of semiconductor in a device in the laboratory, then there's a very rich set of possibilities for these Aharonov-Bohm interactions in that 2-dimensional world. We can have what we call anyons, and the anyons have the property that if we have a system with some number of anyons widely separated from one another, there are many distinct quantum states, which locally look the same. Many states when we compose all the anyons together, but when we look at the anyons one at a time, all of these states look exactly the same. So that means we can use a system of many anyons to encode quantum information in a very robust way. The environment interacting locally with the anyons will not be able to disturb that information. Furthermore, we have a way of processing the information just by performing exchanges of different anyons. So the configuration of the anyons remains the same as it was when I do this exchange, but the collective quantum state of the many anyons changes. And so we can imagine, following Kitaev's proposal, operating a topological quantum computer, which we would initialize by creating pairs of anyons in our two-dimensional system, and then performing a sequence of exchanges of neighboring particles so that the world lines of the anyons in 2 plus 1 dimensional spacetime trace out a braid, and then we could read out the result of the computation by bringing these anyons together in pairs and observing whether those pairs are able to annihilate or not. Now, what's beautiful about this way of implementing quantum computation is that it has an intrinsic resistance to decoherence. As long as we keep the temperature low so we don't have unwanted anyons that are thermally produced diffusing around, and if we keep the anyons far enough apart from one another, except at the very beginning and very end of our computation, so there's no unwanted exchange of quantum numbers between the anyons, then as long as the anyon world lines execute the right braid, we'll get the right result of the computation. So I was very excited by this idea. So I was stirred to write a poem in Alexei's honor. It read in part, Alexei exhibits a knack for persuading that someday we'll crunch quantum data by braiding, with quantum states hidden where no one can see, protected from damage through topology. Anyon, where do you roam? Braid for a while before you go home. And the poem goes on like that, but you get the idea. It's a very beautiful proposal for how to operate a quantum computer, but it too is well ahead of the technology of its time. This is something that we can really realize in the lab. Well, here too, Kitaev had a helpful idea. He proposed a realization of topological quantum computing based on the principle that we can split an electron into two parts. Now that sounds ridiculous because you know an electron is an elementary particle and therefore indivisible. But for an electron living in a highly entangled system, wonderful things can happen, including the splitting of electron into pieces. Here's one way that could occur. We can imagine a quantum wire, which is superconducting. That means it conducts electricity without any dissipation, without any resistance. But as Kitaev observed, there are two types of superconducting wire, the ordinary type and an exotic type called a topological superconductor. And at the boundary between the two types, there lives an object we call a Majorana mode. And now we can imagine adding an extra electron to this segment of topological superconductor wire, and when we do so, that electron dissolves and disappears, leaving no locally discernible trace. But as it does so, the state of the pair of Majorana modes at the two ends of the segment changes. But that's a change that can't be observed locally if we look at the endpoints of the segment one at a time. What has changed is a collective property of the two endpoints. So the information is stored in the type of non-local way, which provides intrinsic protection against decoherence. And experiments have been done probing this type of behavior going back 6 years, and steadily those experiments have improved. But we still don't have completely compelling experimental evidence that this topological storage of quantum information can be realized in the lab. Further experiments are needed. But even if we could do this robust storage of information, we would want more than that. We would want to be able to process that information. And the way that might be done is to consider a network of these one-dimensional quantum wires, which could, say, be built in a two-dimensional plane, with T-junctions, where I can control the position of the boundary between the conventional and topological superconductor with some voltage gate underneath the sample. And that would enable me to move the Majorana modes around, so the one initially on the left could be parked around the corner, the one initially on the right moved to the left, and then we unpark the first one, and that achieves an exchange of the two Majorana modes. That would be braid in a quantum computation, an elementary step in an intrinsically robust computation using Majorana modes. That type of experiment has not yet been successfully carried out, but we're hopeful that it will be done in the next couple of years. And when that happens, it will not just be an intriguing step forward for a potential technology, but I think a fundamental advance in quantum condensed matter physics. Now, I don't want to give the impression that this exotic topological encoding of quantum information is the only way to build a quantum computer, which is being pursued in the laboratory. Quite the contrary. There are many different encodings of qubits that are being vigorously pursued and are advancing steadily. I've already mentioned the possibility of storing a qubit in the polarization of a single photon. We can also have quantum information carried by a single atom, which could be, say, either in its electronic ground state or some long-lived excited state. We could store information in a single electron, encoded in the magnetic moment of the electron, which could be oriented up or down along some axis. So these are two remarkable encodings. In fact, all three of these. Information encoded in a single quantum system, but over decades of technical development, the technology has been developed to control these qubits quite well with existing tools. There are also other types of encoding. For example, encoding a qubit in a superconducting circuit. Now, this is not the type of exotic topological superconducting circuit that I described a moment ago, just an ordinary superconductor. In practice, there are more sophisticated ways of doing it, but to get the idea, we can imagine encoding quantum information in the persistent current in a loop of wire, where the current circulates either clockwise or counterclockwise, corresponding to the two states of the qubit. And that, too, is a remarkable encoding because it involves the collective motion of billions of pairs of electrons, and yet that qubit can be controlled very accurately as though it were a single atom. So where's the technology now? We're actually at kind of a privileged time in the history of quantum technology. We are on the brink of what we call quantum supremacy. We use those words to mean some task we can perform with a quantum device which surpasses what can be done with our best available classical supercomputers. And I thought we should have a word for the era of quantum technology, which is about to dawn, so I made up a word. NISQ, N-I-S-Q. It stands for Noisy Intermediate Scale Quantum. The intermediate scale refers to the number of qubits in the device in question, say 50 to 100 qubits, which is already enough so that we can't, by brute force, simulate what's happening in the quantum device using the best available digital computers. Noisy emphasizes that these NISQ quantum computers will not be error-corrected, and the noise in the qubits will limit their computational power. Now, physicists are excited about the advent of this NISQ technology. It provides us with a new tool for exploring the dynamical properties of a system of many strongly correlated, highly entangled particles. And it might also have, in the relatively near term, useful applications which would be of commercial interest, but we're not really sure about that. We shouldn't think of NISC as something that's going to change the world by itself right away. Instead, it's a step towards more powerful quantum technologies that we expect to arise in the future. I'm confident that eventually quantum technology and quantum computing will have a transformative effect on society, but we're not sure how long that's going to take. It could still be decades before that impact is strongly felt. There's kind of an emerging paradigm for how we might use these near-term quantum computers, NISC devices, a kind of hybrid quantum classical scheme. It makes sense to use our classical processor to the extent that we can and then boost its power by using a quantum processor in addition. And in this hybrid scheme, we would perform some relatively simple quantum computation and then measure all the qubits so we get a classical outcome, then feed those bits to a classical optimizer, which would return instructions about how to modify the quantum computation performed by the quantum processor, and then that cycle would be iterated many times until convergence, with the goal of optimizing some cost function in order to solve an optimization problem. It could be a problem in classical combinatorial optimization, or it could be a quantum problem, like trying to find the ground state of a many-particle quantum system. Now, we actually don't expect quantum computers to be able to give exact solutions to the worst-case instances of the hardest combinatorial search problems, the NP hard problems. But it's possible that a quantum computer will be able to find better approximate solutions or to find approximate solutions faster. Will these NISC devices really be able to outperform the best classical methods we currently have for solving optimization problems? We don't know. It's a lot to ask because these classical methods have been well honed over decades of technical development. So we don't know whether NISC devices will be able to do better, but we're going to try it and see how well it works. Now, these NISC-era quantum devices will not be protected by quantum error correction, and the noise will limit the size of the quantum computations we'll be able to perform with some reasonable signal-to-noise. If we want to scale up to quantum computers that can really solve hard problems, quantum error correction will be essential. But the reason we can't use that in the NISC-era devices is because quantum error correction is very expensive in terms of overhead costs, the need for additional physical qubits and more quantum gates, essentially because encoding the information in that big quantum book requires a lot of additional physical qubits. Now, how big the overhead cost is depends on the algorithm that we're trying to execute and on the quality of the hardware that we're using. But if we consider what it would take to solve some problem that would be useful for chemistry, we probably want greater than 100 very well-protected qubits. And with today's hardware, each one of those well-protected qubits might require hundreds of thousands of physical qubits. So to reach a truly scalable quantum technology, we have far to go from where we're going to be in the next few years with the order of 100 qubits to the million or so physical qubits that it would take to solve really interesting hard problems. And we don't know how long it's going to take to cross that chasm. It could be quite a while. But there are opportunities here for the basic science and engineering. We may be able to hasten the arrival of that fully fault-tolerant quantum computer through advances in the qubit technology, better systems engineering, algorithm design, and advances in the theory of quantum error correction. So I've been emphasizing three main questions about quantum computers. Why do we want to build one? What will we do with it? Well, maybe the best answer we currently have, though there may be much better answers that we haven't yet discovered, is that a quantum computer should be able to simulate efficiently any process that occurs in nature. We don't think that's true of classical digital computers, which are unable to simulate highly entangled quantum systems. Will we really be able to build a large-scale quantum computer? Well, we don't know of any obstacles blocking the way now that we understand the principles of quantum error correction. And how will we build a quantum computer? What will its hardware be like? Well, as I've emphasized, there are a number of approaches to building quantum hardware that are being explored. It's important for the time being to develop different hardware platforms in parallel with one another, because different platforms could have different applications, and because we really don't yet clearly understand which technology has the best prospects in the long run for scalability to large devices. But I'm not really an engineer, I'm a theoretical physicist, so what excites me the most is the ways in which our ideas about quantum information are shedding light, giving us new perspectives on other problems in physics. The way I look at the field of quantum information is that we are still in the very early stages of the exploration of a new frontier of the physical sciences, what we could call the complexity frontier or entanglement frontier. This is different from the short distance frontier we explore in particle physics or the long distance frontier of cosmology. But like those, it's very fundamental and exciting. We are in the process of acquiring and perfecting the tools that we need to build and precisely control highly entangled states of many particles, states so complex that we can simulate them with our best supercomputers, and that opens new opportunities for discovery. It may be particularly noteworthy that there's been a surge of interest in quantum information ideas recently among the community of physicists who are interested in quantum field theory and quantum gravity. These people think that quantum information ideas can be helpful for addressing the problems that they're really interested in. And one of those problems is the difficulty of understanding the quantum behavior of black holes. That's a problem we've been struggling with for decades. And that struggle has given rise to a remarkable idea that we call the holographic principle. The holographic principle asserts that, contrary to naive appearances, the information in a room like this one, encoded in our brains and our smartphones and so on, is actually available, but in some highly scrambled form that's exceedingly hard to read on the boundary of the room, on the walls and the floor and the ceiling. It may not appear that way, but if our ideas about quantum information are on the right track, something like that appears to be so, and it is realized in the toy models of quantum gravity that we've been able to understand so far. And what's particularly interesting is that the geometry in the room, the information about who is sitting in proximity to whom, is encoded in the quantum entanglement in that boundary state. So we may say that we can think of entanglement as the essential ingredient that holds space together, that determines that different points are really connected together by a path in space. So far, you might regard this as just a slogan, but we hope and intend to turn it into a precise understanding of the quantum physics of space-time, and progress is being made in that direction. Recently, we had an event at CalTech, and there was a talk by Robert Digraph, the director of the Institute for Advanced Study, and he gave a talk about how the ideas of theoretical physics are connected to one another, and he concluded with this slide, which I found striking because he chose to put quantum information right at the center of things. And I don't think Digraph would have done that a few years earlier. The idea that quantum information is a unifying principle of physics has really started to get traction only relatively recently. But where I might differ from Digraph is I would erase the word theoretical, because quantum information is an experimental subject. And if it's true, as many of us believe, that quantum space-time geometry should be regarded as an emergent feature arising from quantum entanglement in some underlying quantum system, then we can anticipate that deep insights into the quantum structure of space-time will arise from laboratory experiments studying highly entangled quantum systems. It may be possible on a tabletop in a laboratory at a place like UCLA to build a model space-time that didn't exist before, and by studying its properties, gain deeper insights into the quantum nature of space and time. Whether that prophecy really comes true, we'll have to wait and see. But I think we can say with great confidence that many surprising discoveries await us as we explore the entanglement frontier. Thanks a lot for listening.
Thanks a lot for that really inspiring talk. Are there any questions? Comments? David?
So, in the sense that quantum computing is better than classical computing, is there something else that is equally better than quantum computing? Or is there some metric that you can say quantum computing is the best of computing?
Right, so the question is the separation that I've spoken of between the power of a quantum computer and a classical computer the end of the story? Or could there be a super quantum computer based on laws of physics either now known or to be discovered? So this is a very deep and important question. I would phrase the question this way. Does our current model of a quantum computer, of the type that people are now trying to construct in the lab, does it fully capture the computational power of nature? Or could there be physical processes that surpass what we can do within that quantum computing model? So, of course, the biggest unknown is what about quantum gravity? Is it possible, in particular, to efficiently simulate processes that involve quantum gravity with a quantum computer? Either a yes or no answer to that question, and we don't yet know the answer, would be extremely interesting. If the answer is that it's not possible with a garden variety quantum computer to simulate quantum gravity, that would mean our current model of a quantum computer doesn't fully capture the computational power of nature. The quantum gravity computer might be still more powerful if we can learn how to exploit it. If the answer is yes, we can simulate quantum gravity efficiently with the type of quantum computer we hope to have in the next few decades. That's also quite exciting because it means that we'll be able to explore and learn about quantum gravity using quantum simulators that will be operating in the not-too-distant future. So, we can't lose. I don't know the answer to the question. But either answer is good.
Any more questions?
What's your perspective of the debate and images sort of?
So the question was about a company called D-Wave Technology, which is pursuing a different approach to quantum advantage in processing. I won't go into the story in detail, but what D-Wave has built is what they call a quantum annealer, and its purpose, its goal, is to solve combinatorial search problems by a kind of adiabatic evolution. What the device is designed to do is to find the ground state, or a good approximation to the ground state of a classical spin glass. This is a famous NP-hard problem. And the devices are now of a substantially larger scale than what I described. The circuit-based quantum computers of 50 to 100 qubits, which we're starting to build now, are a lot smaller in terms of number of qubits than the D-Wave machine, which has 2,000 qubits. What is not yet demonstrated by any theoretical or experimental evidence that I know of is that the D-Wave technology really does achieve a speed up compared to the best classical devices running the best algorithms solving the same problem. What has been observed so far is a scaling of the time to solution with the D-Wave device, which matches the scaling with the size of the problem that's achieved by classical algorithms. So I think this quantum annealer approach is extremely interesting. It's an ambitious and potentially revealing physics experiment which should be continued. And as the D-Wave device continues to scale up, as they intend to larger devices, I'll be very interested to see how the performance scales with the size of the problem, and whether, in fact, evidence for the speed up achieved by that technology is eventually observed.
So, say space-time is an emergent phenomenon of entanglement of some fundamental degrees of freedom. Do you have any idea what those degrees of freedom would be, or are they discrete, or like qubits, or a field thing like that?
So I think the question was, if indeed space-time is emergent from some underlying quantum system, what would that quantum system be, which is more fundamental than space-time? So the thing that is best understood currently is sort of a baby version of what I described, discovered by the string theorists, called ADS-CFT duality, where one can consider an ordinary quantum theory without gravity. Technically, it's a conformal field theory. And you can imagine that quantum system residing on the boundary of the space-time, and the bulk geometry inside the space-time is a kind of emergent property arising from entanglement in the quantum field theory, and there's a lot of evidence that that interpretation makes sense. But one might like to go further and generate all of the geometry. In this case, there's just one additional dimension which arises as an emergent property. The bulk space-time has one more dimension than boundary field theory. One proposal for realizing all the dimensions of space from an underlying quantum system is the quantum mechanics of matrices, where the quantum system is one in which there's no geometric locality constraint, but rather you can think of a very big matrix. It has to be very big to encode space-time, where the elements of the matrix are all coupled to one another without any geometric locality constraints. And it's been partially understood, but not nearly so well understood as in the ADS-CFT case, how space-time can arise as an emergent property of matrix quantum mechanics. But there may be other possibilities which we haven't yet properly understood.
I have two sort of related questions about quantum entanglement. So firstly, say suppose you have two particles that are entangled, and if one observer observes one of the particles, does that corrupt or change the system of the other particle as well, even though the other particle has not been observed? And secondly, by the same token, say suppose you have n such particles and one of them decoheres due to environmental interactions, would that corrupt the system of all the other particles?
Right, so let's answer the questions one at a time. So the first question is, if we have two entangled particles and we, let's say, measure or interact with one member of that pair of particles, will that have an instantaneous effect on the quantum state of the second particle? The answer is no. I tried to emphasize that in the talk, that entanglement means a characteristic correlation between those two parts of the system, the two particles, which is different from any correlation that can be realized in a classical system, but it does not involve instantaneous signaling from one system to the other. And your second question was, if we have a many-particle system, which is highly entangled, and one of the particles is damaged or manipulated, how will that affect the remaining n-1 of the n particles? And the answer is the same as the one I just gave. If I look at any observation that can be made on those n-1 particles before I've interacted with the first particle, the outcome of any such measurement before I've touched the first particle and the outcome of any such measurement after I've touched it will be the same. So there is no, again, instantaneous change in the rest of the system when I manipulate one of the particles.
signal that can affect large many signal. If you measure one particle, then you go transmit information. But measuring one, you get away from it.
So I'm going to massage the question a little bit, but I think it's a follow-up to the question I previously answered. Is there some scenario in which, by interacting in some way with half of an entangled system, it produces some change in the other half of the entangled system? Well, let me point to an example, which is the phenomenon of quantum teleportation. So how does quantum teleportation work? We can have shared entanglement between you and me, and I have some quantum state that just arrived in my laboratory, and you want that quantum state in your laboratory, but it's too expensive for me to send it to you directly. So all I can do are operations in my lab, and I can send classical data to you, but I can't afford to send any quantum data to you. And then it's possible for me to make an entangled measurement on this newly arrived system in my half of the entangled state that we share, and send you information about the outcome of that measurement. And when you have access to the classical information that I sent you about my measurement outcome, then you know just what you need to do in your lab to recreate a perfect copy of the unknown quantum state that just arrived in my lab. But if we just made use of the entanglement, without that classical communication, without me sending you information about the outcome of some measurement I made in my lab, then the teleportation doesn't work, and you have exactly the same quantum state in your lab that you had before I did my measurement. It's essential that there be communication between us in order for the information to be transmitted. What's wonderful about teleportation is that I can send an unknown quantum state to you with just, if it's the quantum state of a single qubit, with just 2 bits of classical data. But the communication is still essential. Well, entanglement swapping, same story. So the question was, is the same true for entanglement swapping? The way entanglement swapping works is that now we have 3 parties. So we'll bring Zvi into the game. And Zvi and I have an entangled pair of qubits. And you and Zvi have an entangled pair of qubits. And you and I want to have an entangled pair. So what our buddy does is he performs some entangled measurement on the 2 halves of the entangled state, one shared with you and one shared with me. And that by itself doesn't change what we have in our labs. He can then send the information to us about the outcome of this entangled measurement, and then you and I share the entanglement. Yeah, but he has to send classical information in that case as well. And so, in fact, this idea of entanglement swapping is how we propose to distribute entanglement over very long distances around the globe eventually. Because we should be able to establish entangled pairs, say, by sending photons and optical fibers, shared by parties who are tens of kilometers apart. But if I want to boost that to much longer distances, a way to do it is by means of entanglement swapping, assuming that we have the ability to get very good entangled pairs shared among stations that are tens of kilometers apart, and there are protocols for doing that. So this idea of entanglement swapping may be important for the technology of distributing entanglement around the world. But it couldn't work unless we had classical communication as well as shared entanglement.
Let's thank Jonathan.